Welcome to DreamLab Knowledge, where we turn our gaze upward to explore the cosmic home we inhabit but barely understand. Tonight, we embark on a journey through the Milky Way, our galaxy, our stellar neighborhood, our cosmic address in an incomprehensibly vast universe. Close your eyes for a moment and imagine yourself floating high above Earth, rising beyond the blue atmosphere, past the moon, beyond the orbits of the planets, until the entire solar system becomes a tiny point of light. Keep rising. The stars that seem so fixed and eternal begin to move, revealing their true nature as distant suns in motion. And then you see it, a magnificent spiral of light stretching across the darkness, hundreds of billions of stars arranged in graceful arms that sweep through space like luminous rivers. This is our galaxy. This is home. Yet for all its beauty, for all the centuries we have gazed upon the Milky Way's pale band, stretching across the night sky, this galaxy remains deeply mysterious. We are cosmic archaeologists, piecing together its history from the light of ancient stars. We are detectives, tracking the movements of invisible matter that outweighs everything we can see. We are explorers on the inside of an immense structure, trying to map its contours without ever stepping outside to see the whole picture. Tonight, we will venture into the secrets of the Milky Way. Secrets that challenge our understanding of physics, secrets that reveal a violent and dramatic past, secrets that hint at an equally dramatic future. The architecture of home. Let us begin with what we know about the grand architecture of our cosmic dwelling. The Milky Way is a barred spiral galaxy roughly 100,000 light-years across, though recent measurements suggest it may extend to 160,000 light-years. Light itself, traveling at 186,000 miles per second, takes 100,000 years to cross from edge to edge. At its heart lies a dense bulge of older stars shaped like a peanut, measuring about 10,000 light-years across. The bulge glows with yellowish, reddish light from countless red giants and supergiants, elderly stars born more than 10 billion years ago. The bulge contains approximately 10 billion stars. If Earth orbited a star there, the night sky would blaze with 1 million stars as bright as Sirius, creating perpetual twilight. Through this bulge runs a bar, a linear concentration of stars and gas roughly 27,000 light-years long. The bar rotates as a coherent structure, shepherding gas toward the galactic center and influencing the spiral arms. From the bar's ends, the major spiral arms begin their sweep through the disk. The disk itself is complex and layered. The thin disk, perhaps 700 light-years thick at our location, contains the youngest stars, the densest gas and dust, and nearly all ongoing star formation. Here, molecular clouds collapse to birth new stellar generations. The thin disk is dynamic, constantly recycling material between stars and the interstellar medium. Embedded within lies a thicker component, extending about 3,000 light-years vertically, populated by older stars with different orbital characteristics. These thick disk stars have lower metallicities, reflecting formation from less enriched gas. They're several billion years older and orbit with higher velocities perpendicular to the plane, suggesting formation during a more violent epoch, perhaps heated by ancient mergers. Recent research revealed even older populations. In October 2024, astronomers announced Pangu, stars that formed more than 13 billion years ago, the oldest surviving disk population, With an estimated 2 billion solar masses, its survival through subsequent mergers suggests the young Milky Way was already massive enough to dominate smaller infalling systems. Beyond the visible disk stretches the stellar halo, extending perhaps 100,000 light-years from the galactic center, though stars have been detected at twice that distance. This halo hosts the galaxy's most ancient citizens, stars formed when the universe was less than 1 billion years old. Many halo stars have metallicities, 100th or 1000th that of the Sun. The halo also contains globular clusters, compact spherical collections of ancient stars. The Milky Way has approximately 150 to 200 known globular clusters, among the oldest objects in the galaxy, with ages approaching 13 billion years. But the stellar halo represents only 1% of the galaxy's stellar mass. Yet it's crucial because almost all halo stars were born in other galaxies, later torn apart and consumed by the Milky Way's gravity. The halo is a graveyard of galaxies. Surrounding everything visible lies the dark matter halo, extending perhaps 500,000 light-years or more, and containing roughly 5 times more mass than all stars, gas, and dust combined. This is the gravitational skeleton upon which the visible galaxy hangs. The Milky Way's total mass, including dark matter, is estimated between 1 and 2 trillion solar masses. Our Sun resides at approximately 27,000 light-years from the galactic center, embedded in the thin disk in the Orion Arm, a minor spur. This suburban location may be precisely what allowed complex life to emerge on Earth. From our location, we complete one orbit around the galactic center approximately every 230 million years, a cosmic year. We're always moving at roughly 220 kilometers per second relative to the galactic center, yet we feel nothing. Beyond the visible disk stretches the stellar halo, a roughly spherical region that extends perhaps 100,000 light-years from the galactic center, though some stars have been detected even farther out. This halo is home to the galaxy's most ancient citizens, stars that formed when the universe was less than 1 billion years old, globular clusters that contain hundreds of thousands of primordial stars tightly bound by gravity, and the ghostly streams of stars that trace the violent history of galactic cannibalism. Here, in the outer reaches of our galaxy, you can still find the oldest stars in our cosmic neighborhood, stars that remember the epoch when galaxies were first taking shape. But the stellar halo, for all its ancient grandeur, represents only a tiny fraction of the Milky Way's true extent. Surrounding everything we can see lies an even more mysterious component, the dark matter halo. This invisible structure, detectable only through its gravitational influence, extends perhaps 500,000 light-years or more from the galactic center and contains roughly 5 times more mass than all the stars, gas, and dust combined. It is the gravitational skeleton upon which the visible galaxy hangs, the hidden framework that keeps our galaxy from flying apart as it spins through space. Our Sun, an ordinary yellow dwarf star about halfway through its 10 billion year lifetime, resides in a rather unremarkable location. We orbit the galactic center at a distance of approximately 27,000 light-years, embedded in the thin disk, positioned between 2 major spiral arms. We are, in cosmic terms, suburban residents, living in the galactic outskirts far from the crowded and energetic center. This location is neither privileged nor remarkable, yet it may be precisely what allowed complex life to emerge on Earth. The galactic center, with its dense packing of stars and the violent eruptions from the supermassive black hole, would have subjected any planets to far more radiation and gravitational disruptions. Out here in the suburbs, life had room to breathe and time to evolve. From our location, we complete one orbit around the galactic center approximately every 230 million years, a span of time called a cosmic year or a galactic year. Think about that for a moment. The last time our solar system was in this position in its orbit, dinosaurs had not yet appeared on Earth. The time before that, the first multicellular life was just beginning to colonize the land. We are always moving, always traveling through space at speeds that would seem incomprehensible if we could feel them. Our sun carries us along at roughly 500,000 miles per hour relative to the galactic center, yet we feel nothing. The stars we see in the night sky are also in motion, each following its own orbital path through the galaxy's gravitational field, creating a grand cosmic choreography that unfolds over timescales that dwarf human history. The heart of darkness. The heart of darkness. At the very center of our galaxy lies something both fascinating and terrifying. A supermassive black hole designated Sagittarius A, or SAGI-A for short. Pronounced Sagittarius A star, this cosmic monster contains the mass of approximately 4.3 million suns, yet it occupies a region of space smaller than Mercury's orbit around the sun. To appreciate the density this implies, imagine compressing 4 million suns, each already unimaginably dense by human standards, into a sphere roughly 44 million kilometers across. The resulting gravitational field is so intense that at the event horizon, the escape velocity exceeds the speed of light. Nothing, not even light itself, can escape once it crosses this boundary, which is why we call it a black hole. The black hole itself is invisible, as black holes must be. Their defining characteristic is that they trap light completely. But we know Sagittarius A exists because of what we can observe around it. The discovery of the black hole is a story of patient, meticulous observation spanning decades. In 1974, astronomers Bruce Ballack and Robert Brown detected a bright radio source at the galactic center. They named it Sagittarius A, after the constellation where it appears in our sky. The asterisk was added later to distinguish the compact, point-like radio source from the larger diffuse emission in the region. But the definitive proof of the black hole's existence came from tracking the orbits of stars near the galactic center. Starting in the early 1990s, two teams of astronomers, one led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany, and another led by Andrea Ghez at UCLA, began monitoring stars in the immediate vicinity of Sagittarius A. Using adaptive optics and sophisticated infrared telescopes to peer through the obscuring dust that blocks visible light from the galactic center, they measured the positions and velocities of individual stars with extraordinary precision. What they discovered was astonishing. Stars near the galactic center orbit at incredible speeds around an invisible point. The most studied of these stars is designated S2, sometimes called S02 in the German team's nomenclature. This star completes one full orbit around the black hole every 16 years, and at its closest approach, a distance of only 17 light hours from the black hole, it reaches speeds of approximately 8,000 kilometers per second, nearly 3% of the speed of light. These are not human scale velocities we're talking about. This is a star with a mass perhaps 15 times that of our sun, moving so fast that it could travel from Earth to the moon in under 50 seconds. By carefully measuring the positions and velocities of S2 and other stars over many years, astronomers were able to apply Kepler's laws of orbital motion to calculate the mass of the invisible object they orbit. The mathematics are straightforward. If you know how fast something is moving and how far away it is, you can determine how much mass is pulling on it. The conclusion was inescapable. The central object contains approximately 4 million solar masses confined to a region smaller than our solar system. No configuration of stars or any normal matter could be so compact. Only a supermassive black hole fits the observations. For this work, demonstrating that Sagittarius A is a supermassive compact object for which a black hole was the only plausible explanation, Genzel and Gears shared the 2020 Nobel Prize in Physics, but the achievements didn't stop there. In 2022, the Event Horizon Telescope collaboration achieved something that many thought impossible. They captured the first direct image of Sagittarius A. This wasn't actually an image of the black hole itself. You fundamentally cannot photograph something that emits no light. Instead, what they imaged was the ring of superheated matter that surrounds the black hole, viewed against the shadow cast by the event horizon itself. Creating this image required an extraordinary feat of engineering and international cooperation. The Event Horizon Telescope is not a single instrument, but rather a global array of radio telescopes coordinated to work together as a single telescope the size of Earth. 8 observatories across the planet, from Hawaii to Chile, from Arizona to Antarctica, simultaneously observed Sagittarius A over several nights in April 2017. Each observatory recorded radio waves at millimeter wavelengths, and then the data from all sites was carefully synchronized and combined using a technique called very long baseline interferometry. The challenge of imaging Sagittarius A was immense. The black hole is relatively small as these objects go, spanning only about 24 million kilometers across at the event horizon. From Earth, 27,000 light years away, this corresponds to an angular size of only about 50 microarcseconds, roughly equivalent to viewing a donut on the moon from Earth. This is far beyond the resolving power of any single telescope, which is why linking telescopes across the globe was necessary. But size wasn't the only challenge. Unlike M87, the first black hole imaged by the Event Horizon Telescope in 2019, Sagittarius A, is a much more difficult target because it's much more variable on short timescales. M87 is about 1,500 times more massive than Sora, which means matter orbits it much more slowly. The timescale for changes is days to weeks for M87, allowing for relatively stable imaging. But for Sagittarius A, matter whips around the event horizon in minutes, like trying to photograph a squirming toddler rather than a still portrait subject. The view changes dramatically from minute to minute as hot clumps of gas orbit the black hole at relativistic speeds. To overcome this challenge, the team collected data for many hours and then used sophisticated algorithms to reconstruct thousands of different images from the data. They averaged these reconstructions together selecting features that appeared consistently across different methods and different subsets of the data. The final image represents an average of these thousands of possibilities, showing what Sagittarius A typically looks like, even though its appearance is constantly changing. The result is a glowing orange ring, approximately 52 microarc seconds across, with a dark region in the center. This dark region is the shadow of the black hole, not the event horizon itself, but the region within which the black hole's gravity is so strong that light cannot escape to reach us. The bright ring is emission from gas and dust, heated to billions of degrees as it spirals inward toward the event horizon. This material has been accelerated to a significant fraction of the speed of light, and as it moves, it generates intense magnetic fields and emits synchrotron radiation that we detect as radio waves. The image confirmed predictions from Einstein's general theory of relativity about how strong gravitational fields bend light. The black hole's gravity acts as a lens, bending the paths of photons and creating the ring-like appearance. Light from material behind the black hole is bent around it, allowing us to see both the near side and the far side of the accretion structure simultaneously. The image also showed that the ring is not uniform in brightness. There are bright spots and darker regions, reflecting the turbulent, chaotic nature of the inflowing material. Despite its tremendous mass, Sagittarius A is remarkably quiet compared to black holes in other galaxies. It accretes matter at an extraordinarily low rate, only about 100,000th of a solar mass per year. For comparison, if you could somehow capture all the matter currently falling into Sagittarius A and form it into stars, you would produce roughly one sun mass star every 100,000 years. This makes it what astronomers call a quiescent or inactive black hole. In other galaxies, supermassive black holes can consume vast amounts of material, generating enough energy to outshine the entire galaxy and launching enormous jets of particles and radiation that extend for millions of light years. Our galactic black hole, by contrast, barely whispers. But it hasn't always been so quiet. Multiple lines of evidence suggest that Sagittarius A has experienced dramatic outbursts in the relatively recent past. In 2023, observations from NASA's Imaging X-ray Polarimetry Explorer, XPE for short, revealed evidence of a significant outburst approximately 200 years ago, around the time of the late 1700s on Earth. The evidence came from what astronomers call light echoes. Imagine shouting toward a distant canyon wall and hearing your voice bounce back seconds later. Light echoes work on a similar principle, but on cosmic scales. When Sagittarius A experienced its outburst 2 centuries ago, it emitted intense X-ray radiation that traveled outward in all directions. Some of this radiation traveled directly toward Earth and arrived long ago, but we weren't looking with the right instruments to see it. Other X-rays traveled outward in different directions, striking giant molecular clouds located thousands of light years from the galactic center. When these X-rays hit the clouds, they caused the cloud's atoms to fluoresce, emitting X-rays of their own in response. These secondary X-rays are now reaching Earth, allowing us to see an echo of an event that occurred 200 years ago. By analyzing the polarization and spectrum of these X-rays, astronomers can deduce properties of the original outburst. The data suggests that Sagittarius A was at least 1 million times brighter 2 centuries ago than it is today. A dramatic change that hints at the black hole's more violent past. What caused this outburst? Perhaps a star or a particularly massive gas cloud wandered too close and was torn apart by tidal forces, providing the black hole with a sudden feast of material. Or perhaps it was part of a cyclical pattern of activity and quiescence that we're only beginning to understand. Even more recently, in 2024, the Event Horizon Telescope made another breakthrough. They imaged Sagittarius A in polarized light. Polarization, the orientation of light waves, provides information about magnetic fields because magnetic fields cause the light emitted by charged particles to become polarized in specific directions. The polarized image revealed strong, organized magnetic fields spiraling outward from the edge of the event horizon, similar to those observed around M87. The discovery of these magnetic fields is significant because it suggests that Sagittarius A may harbor a dormant jet, a narrow beam of particles and energy that could be launched along the black hole's rotation axis. Many active black holes produce jets that extend for millions of light years, powered by magnetic fields that extract rotational energy from the spinning black hole and channel it into collimated outflows. The magnetic field structure around Sagittarius A looks similar to that around M87, which does produce a visible jet. This suggests that our galactic black hole may have launched jets in the past, and under the right conditions, might do so again. Computer models of the Milky Way's center support this idea. Simulations suggest that just a few million years ago, a blink of an eye in cosmic time, Sagittarius A may have been actively producing jets that carved out cavities in the surrounding gas and accelerated particles to enormous energies. These ancient jets might be responsible for some of the high energy phenomena we observe near the galactic center today, including the mysterious gamma ray emission and the enormous Fermi bubbles that extend above and below the galactic plane. The region immediately surrounding Sagittarius A is an environment of truly extreme conditions. Within the central few light years, stars orbit at velocities that seem impossible, subjected to tidal forces that would tear apart any normal celestial body. The star S2, during its closest approach, experiences gravitational forces about 10,000 times stronger than what Earth experiences from the Sun. At that distance, the curvature of space-time is so severe that time itself flows at a measurably different rate compared to locations farther from the black hole, a manifestation of gravitational time dilation predicted by general relativity. Molecular clouds near the galactic center glow with X-rays and gamma rays, energized by cosmic rays, subatomic particles accelerated to nearly the speed of light. These cosmic rays are produced by violent processes, supernova explosions, colliding stellar winds, and possibly acceleration in the strong magnetic fields near the black hole itself. The density of cosmic rays in the galactic center is much higher than in our solar neighborhood, creating a radiation environment that would be lethal to any form of life as we know it. The immediate vicinity of Sagittarius A also contains mysterious objects that don't fit into our standard categories. Astronomers have identified several so-called G objects, structures that appear in some observations as dusty gas clouds, but in other observations show characteristics more typical of stars. The prototype, G2, was discovered in 2004 and closely monitored as it made its closest approach to the black hole in 2014. Many astronomers predicted it would be torn apart and consumed. producing a dramatic flare. Instead, G2 survived the encounter, though it was stretched and distorted by tidal forces. This unexpected resilience suggests it might not be a simple gas cloud, but rather a star surrounded by a dusty envelope, or perhaps a binary star system that has been partially disrupted. In 2024, astronomers made an even more surprising discovery: a young binary star system orbiting perilously close to Sagittarius A. This double star, designated D9F, is remarkable because binary systems were thought to be impossible to form in such a hostile environment. The intense tidal forces near the black hole should rip apart any loosely bound system, preventing binaries from forming or tearing apart any that drift too close. Yet here is a pair of stars, apparently relatively young, formed within the last few million years, somehow surviving in a realm that should have destroyed them. Their existence challenges our understanding of star formation near supermassive black holes and suggests that even in the most extreme environments imaginable, nature finds ways to create and preserve structure. The stars orbiting Sagittarius A are not typical stellar populations. Many are massive, hot blue stars, precisely the type of star that should not exist in the galactic center. These stars live for only a few million years before exploding as supernovae, yet we observe many of them in the inner parsec around the black hole. This suggests they must have formed in situ, born from gas clouds near the black hole despite the hostile environment. But how molecular clouds can collapse to form stars in the presence of such strong tidal forces remains an active area of research. The stars near the black hole are organized into at least two distinct stellar disks or clusters. These structures contain dozens of massive young stars that orbit the black hole on roughly coplanar paths, suggesting they formed from larger disk-like structures of gas that somehow maintained coherence despite the tidal stresses. The origin of these stellar disks is debated, with models invoking everything from the tidal disruption of a giant molecular cloud to the migration of an entire star cluster into the galactic center region. Additionally, the galactic center hosts a population of hypervelocity stars, stars moving so fast that they will eventually escape the Milky Way's gravitational pull entirely. These stars were likely accelerated through gravitational interactions with the central black hole, possibly involving binary star systems where one member was captured by the black hole while the other was flung outward at tremendous speed. Some hypervelocity stars are moving at over 1,000 kilometers per second relative to the galaxy, fast enough to interreach intergalactic space within a few million years. The environment near Sagittarius A is also a laboratory for testing general relativity in extreme conditions. When S2 made its closest approach in 2018, astronomers carefully measured how light from the star was redshifted by the black hole's gravity, a phenomenon called gravitational redshift. They also looked for relativistic effects on the star's orbit, such as the precession of its orbital ellipse. Both effects were detected, and they matched Einstein's predictions with remarkable precision. These observations represent some of the strongest tests of general relativity in strong gravitational fields, confirming that our understanding of gravity remains accurate even in the most extreme environments we can observe. Looking ahead, astronomers are planning even more ambitious observations of the galactic center. Future upgrades to the Event Horizon Telescope will add more stations and improve sensitivity, potentially allowing real-time movies of material orbiting Sagittarius A rather than just static images. These observations could reveal the dynamics of accretion in unprecedented detail, showing how matter spirals inward, how it varies with time, and how magnetic fields shape the flow. We may eventually be able to detect the shadow of a stellar mass black hole passing in front of Sagittarius A, or observe the tidal disruption of a star in real time as it's torn apart by the black hole's gravity. Each new observation brings us closer to understanding this exotic object at our galaxy's heart, a massive region of space-time so warped that it defies our everyday intuition, yet obeys with perfect precision the mathematical elegance of Einstein's field equations. For decades, astronomers have tracked the orbits of stars near the galactic center. These stars, particularly one designated S2, swing around an invisible point in looping orbits that approach astounding speeds. S2 completes one orbit every 16 years, and at its closest approach to the black hole, it travels at nearly 3% of the speed of light. By carefully measuring the positions and velocities of such stars over many years, astronomers have been able to calculate the mass of the invisible object they orbit with remarkable precision. The conclusion is inescapable. Only a supermassive black hole could explain the observations. This work earned Reinhard Genzel and Andrea Ghez the 2020 Nobel Prize in Physics. In 2022, the Event Horizon Telescope collaboration achieved something remarkable. They captured the first direct image of Sagittarius A. This wasn't actually an image of the black hole itself, you can't photograph darkness, but rather an image of the glowing ring of superheated matter that surrounds it. This ring appears as a result of light being bent by the black hole's immense gravity, and the dark region in the center is the shadow of the event horizon, the point of no return. Creating this image required coordinating 8 radio observatories around the world to effectively create a telescope the size of Earth itself. The resulting image shows a bright donut-shaped ring approximately 52 microarcs seconds across, about the apparent size of a donut on the moon, as seen from Earth. What makes this achievement even more remarkable is the challenge involved. Unlike M87, the first black hole ever imaged by the Event Horizon Telescope, Sagittarius A, is a much more difficult target. It's smaller, which means gas and dust orbit it much faster. The material around M87 takes days or weeks to complete an orbit, while material around SGR-A orbits in mere minutes. This means the image changes drastically on very short timescales, like trying to photograph a squirming child. The final image represents an average of thousands of different reconstructions, each attempting to capture a moment of stability in this dynamic system. Despite its tremendous mass, Sagittarius A is remarkably quiet compared to black holes in other galaxies. It accretes matter at an extraordinarily low rate, only about 100,000th of a solar mass per year. This makes it what astronomers call a quiescent, or inactive black hole. In other galaxies, supermassive black holes can consume vast amounts of material, generating enough energy to outshine the entire galaxy and launching enormous jets of particles and radiation that extend for millions of light years. Our galactic black hole, by contrast, barely whispers. But it hasn't always been so quiet. In 2023, observations from NASA's IXP telescope revealed evidence that Sagittarius A experienced a dramatic outburst approximately 200 years ago, around the time of the American Revolution on Earth. The evidence came from X-ray light echoing from giant molecular clouds near the galactic center, like sound bouncing off canyon walls. The intensity of this echo suggests that the black hole briefly blazed with activity, perhaps devouring a particularly large clump of gas or even a star that wandered too close. For a brief cosmic moment, our galaxy's heart awoke, then returned to its slumber. Recent observations have also revealed strong magnetic fields spiraling outward from the edge of Sagittarius A, similar to those seen around the supermassive black hole in the M87 galaxy. These magnetic fields may be the remnants of ancient jets, powerful beams of particles and energy that the black hole launched into space millions of years ago. Computer models suggest that our galactic center may have hosted such jets in the recent past, cosmic geysers that would have dramatically altered the environment near the galactic center. If so, then the quiescent monster we observe today is merely resting between episodes of violence. Around the black hole lies a region of truly extreme conditions. Within the central few light years, stars orbit at velocities that seem impossible, subjected to tidal forces that would tear apart any normal celestial body. Molecular clouds glow with X-rays and gamma rays, generated by cosmic rays. Particles accelerated to nearly the speed of light. Magnetic fields twist and writhe through space. Time itself flows at different rates depending on how deep into the gravitational well one descends. This is a laboratory of extreme physics, a place where Einstein's general relativity is tested to its limits, and where the boundary between the predictable and the bizarre becomes razor thin. One of the most intriguing recent discoveries involves mysterious objects designated as G objects. These strange structures appear as dusty gas clouds, but emit light in specific frequencies that suggest they contain hidden stars. Some astronomers believe they may be the disrupted remnants of binary star systems, torn apart by the black hole's tidal forces, but not completely destroyed. Others suggest they might be gas clouds that have collapsed and formed new stars. Whatever they are, they represent a population of objects unlike anything seen elsewhere in the galaxy, creatures unique to the extreme environment near the black hole. In 2024, astronomers discovered something even more surprising: a young double-star system orbiting perilously close to Sagittarius A. Binary stars had been thought impossible to form in such a hostile environment. The intense tidal forces near the black hole should rip apart any loosely bound system. Yet here was a pair of stars, relatively young, somehow surviving in a realm that should have destroyed them. Their existence challenges our understanding of star formation near supermassive black holes and suggests that even in the most extreme environments, nature finds ways to create and preserve structure. The invisible skeleton. Perhaps the greatest mystery of the Milky Way is also the most fundamental. What is it mostly made of? The answer is as humbling as it is mysterious. All the stars we see sparkling in the night sky, all the gas and dust clouds where stars are born, all the planets and asteroids and comets, all the black holes and neutron stars and white dwarfs, all of this normal matter, everything that emits or reflects or absorbs light, everything we can detect with any form of electromagnetic radiation. accounts for only about 15% of the galaxy's total mass. The remaining 85% is dark matter, a substance that does not emit, absorb, or reflect light of any kind, whose presence is known only through its gravitational effects on the matter we can see. The story of dark matter begins with rotation curves, graphs that show how fast objects orbit as a function of their distance from the galactic center. According to Newton's laws of motion and gravity, if all the mass in a galaxy was contained in the stars and gas we can see, then stars farther from the center should orbit more slowly, just as planets farther from the sun orbit more slowly. This is simply a consequence of how gravity weakens with distance. We can calculate what the rotation curve should look like based on the distribution of visible matter, and the result is clear. Velocities should decline steadily at large distances from the galactic center. But when astronomers measured the actual velocities of stars at different distances from galactic centers, they found something completely unexpected. Starting in the 1970s, Vera Rubin and Kent Ford used optical telescopes to measure the rotation curves of spiral galaxies, while radio astronomers measured the velocities of neutral hydrogen gas that extends beyond the visible stars. What they discovered revolutionized our understanding of the universe. The rotation curves don't decline as predicted. Instead, they flatten out, remaining roughly constant even at the outermost regions of galaxies where very few stars are visible. Stars at the edge of galaxies orbit at nearly the same speed as stars closer to the center. This observation is only possible if there is a vast halo of unseen mass extending far beyond the visible galaxy. It's gravity keeping the outer stars moving fast enough that they don't fall inward toward the galactic center. The amount of this unseen mass must be enormous, roughly 5 to 10 times the mass of all the visible matter. Initially, some astronomers hoped that this might be explained by undetected normal matter, dim red dwarf stars too faint to see, or perhaps black holes, or neutron stars scattered throughout the galaxy. But every attempt to detect sufficient amounts of normal dark matter failed. The missing mass is not made of protons and neutrons like the matter we're familiar with. It's something else entirely. In our own Milky Way, this dark matter halo is thought to extend perhaps 500,000 light years from the galactic center, roughly 5 times the diameter of the visible stellar disk, and possibly much farther. Some estimates suggest the halo might reach out to 1 million light years or more before merging with the halos of neighboring galaxies in the local group. The total mass contained in this invisible structure is estimated at between 1 and 2 trillion solar masses, though the exact value remains uncertain. This uncertainty reflects a profound difficulty. We are trying to weigh something we cannot see, detect only through its influence on things we can observe, and the more distant the tracer objects we use, the less certain we can be about their properties and motions. Different methods yield somewhat different estimates of the Milky Way's dark matter mass. One approach uses the velocities of satellite galaxies, the dozens of small galaxies that orbit the Milky Way like moons around a planet. By measuring how fast these satellites move and how far out they orbit, astronomers can estimate the total mass needed to keep them bound. Another approach uses globular clusters, ancient spherical collections of stars that orbit through the galactic halo. Yet another method tracks stellar streams, long tendrils of stars that were torn from disrupted dwarf galaxies and now trace out orbits through the halo. Each method has its own systematic uncertainties and potential biases, and the results don't always agree perfectly. Recent research has revealed that this dark matter halo may not be spherical, as once assumed. In September 2023, astronomers from the Harvard-Smithsonian Center for Astrophysics published groundbreaking work showing that the Milky Way's dark matter halo is tilted and elongated, shaped somewhat like a football or a zeppelin rather than a perfect sphere. This discovery emerged from careful analysis of the stellar halo, the sparse collection of visible stars that orbit in the outer regions of the galaxy. By measuring the positions, velocities, and chemical compositions of these stars, the researchers were able to map out the three-dimensional shape of the stellar halo and found it to be tilted at an angle relative to the galactic disk. The crucial insight was that the dark matter halo should have roughly the same shape as the stellar halo, because both formed through similar processes and both respond to the same gravitational forces. If the stellar halo is tilted and elongated, the dark matter halo should be too. The team then used computer models to calculate what would happen to the galactic disk if it was embedded in such a tilted halo. The models predicted that the disk should warp at its edges, bending upward on one side and downward on the other, exactly matching the observed warp in the Milky Way's outer disk. This was a striking confirmation that the dark matter halo really does have the inferred shape. The tilted, elongated shape of the halo also provides crucial clues about the galaxy's formation history. If the Milky Way had formed in isolation, without major disruptions, its dark matter halo would likely be more spherical and aligned with the stellar disk. The fact that it's tilted suggests a violent past, evidence that our galaxy experienced major collisions with other galaxies. Each collision would have added mass and angular momentum in specific directions, gradually warping and tilting the dark matter distribution. The shape of the invisible halo thus preserves a record of ancient galactic violence, written in the distribution of matter we cannot see, but whose gravity shapes everything we can observe. This discovery also has implications for the nature of dark matter itself. The fact that the halo is not perfectly spherical provides constraints on how dark matter particles interact with each other. If dark matter particles could collide and scatter off each other frequently, like atoms in a gas, the halo would tend to relax into a more spherical configuration over time. The observed elongated, tilted shape suggests there are limits to how much dark matter can interact with itself, providing clues to its particle nature. One of the most exciting recent developments in dark matter research involves potential direct detection of dark matter through its particle interactions. For decades, scientists have observed an excess of gamma rays emanating from the galactic center, a diffuse glow that cannot be fully explained by known astrophysical sources. Some theoretical models suggest this could be the signature of dark matter particles annihilating when they collide with each other. If dark matter consists of particles that are their own antiparticles, such as hypothetical weakly interacting massive particles, or WIMPs, then when two dark matter particles meet, they would annihilate completely, converting their mass into energy in the form of gamma rays and other particles. In November 2025, a study published in the BBC Science Focus reported remarkable new observations from NASA's Fermi Gamma Ray Space Telescope, revealing a mysterious halo-like glow of gamma rays around the Milky Way. This glow extends into the halo above and below the galactic disk and peaks sharply at energies of about 20 giga electron volts, 20 billion electron volts, an extraordinarily high energy for individual photons. This energy matches predictions for what would be produced if WIMPs with a specific mass were annihilating in our galaxy's dark matter halo. If confirmed as a dark matter signature, this would represent the first detection of dark matter through means other than its gravitational effects, a breakthrough that would revolutionize our understanding of the universe's composition. The lead researcher, Professor Tomonori Totani from the University of Tokyo, used 15 years of data from the Fermi telescope, carefully modeling and subtracting all known sources of gamma rays, interactions between cosmic rays and interstellar gas, emission from pulsars and other compact objects, and even the enormous Fermi bubbles that extend above and below the galactic center. After accounting for all these sources, a residual component remained, a halo of gamma ray emission that couldn't be explained by conventional astrophysics. The energy spectrum and spatial distribution of this emission matched predictions from dark matter annihilation models with remarkable precision. However, alternative explanations remain. Some astronomers suggest the excess gamma rays could come from a previously unrecognized population of millisecond pulsars, rapidly spinning neutron stars that emit beams of radiation like cosmic lighthouses. Thousands of such pulsars might exist in the galactic halo, each too faint to detect individually but collectively producing the observed gamma ray signal. Others propose contributions from cosmic ray interactions or other astrophysical processes we haven't fully characterized. Distinguishing between these possibilities requires careful modeling of all potential sources and additional observations at different wavelengths and from different locations. The strongest evidence for or against the dark matter interpretation will likely come from observations of the Milky Way's dwarf satellite galaxies. These small galaxies are thought to be extremely rich in dark matter relative to normal matter, with mass to light ratios sometimes exceeding 1,000 to 1. This makes them potentially excellent laboratories for detecting dark matter signals with minimal contamination from ordinary astrophysical sources. If the gamma ray excess is indeed from dark matter annihilation, similar signals should appear in these dwarf galaxies. If it's from astrophysical sources like pulsars, the signals might differ or be absent. Current and future gamma ray observatories are searching these dwarf galaxies with unprecedented sensitivity. Another avenue for dark matter detection involves direct detection experiments here on Earth. Dozens of underground laboratories around the world host experiments designed to catch dark matter particles as they pass through detectors. These experiments use various target materials, liquid xenon, liquid argon, germanium crystals, and others, and operate deep underground to shield them from cosmic ray backgrounds. The idea is that if a dark matter particle collides with an atomic nucleus in the detector, it will impart a tiny amount of energy that can be measured. So far, despite decades of increasingly sensitive searches, no definitive dark matter particle detection has been confirmed. The null results place increasingly stringent limits on the properties dark matter particles can have, ruling out whole classes of theoretical candidates. Yet another approach involves producing dark matter at particle colliders like the Large Hadron Collider. If dark matter particles can be created through high-energy collisions between ordinary particles, they would immediately escape the detector without leaving a trace, because dark matter doesn't interact with the detector material. but their presence could be inferred from missing energy and momentum. Again, despite careful searches, no clear dark matter production signal has been identified. The nature of dark matter remains one of the most profound mysteries in physics. Is it composed of particles? If so, what kind? The most popular candidates are WIMPs, but other possibilities include axions, sterile neutrinos, or even primordial black holes formed in the early universe. Why doesn't dark matter interact with light? The standard model of particle physics includes no particles with the right properties to be dark matter, suggesting new physics beyond our current theories. Why is there so much more dark matter than normal matter in the universe? The processes that created both types of matter in the early universe must have favored dark matter by a factor of 5 to 1 for reasons we don't understand. Despite decades of sophisticated experiments and observations, dark matter remains stubbornly hidden from direct detection. We can map its distribution through gravitational effects. We can infer its properties through its influence on galaxy formation and large-scale structure. We can detect its presence in the rotation curves of galaxies, in gravitational lensing of distant light, in the motions of galaxy clusters. But we cannot touch it, cannot capture it in our detectors, cannot even say with certainty what it is. The universe is constructed on an invisible scaffold we can barely perceive, held together by forces we don't understand, made of material we've never directly detected. Imagining that we understand our galaxy when we can only see 15% of its mass is like claiming to understand a house after seeing only the paint on the walls, with no knowledge of the foundations, the framing, the plumbing, and the electrical systems that make it function. Some physicists have proposed radical alternatives to dark matter. Perhaps, they suggest, our understanding of gravity itself is incomplete. Perhaps the laws of gravity that work well in the solar system need modification on galactic scales. These modified Newtonian dynamics theories, or MOND, attempt to reproduce the observed rotation curves without invoking dark matter. While MOND can successfully explain galaxy rotation curves, it struggles to explain other observations, like gravitational lensing and the large-scale structure of the universe. Most physicists favor dark matter as the explanation, but the debate continues, driven by our frustration at being unable to detect dark matter particles directly after decades of trying. Recent observations have also revealed structure within the dark matter halo. Computer simulations of galaxy formation predict that dark matter should clump into subhalos, smaller concentrations of dark matter that survive as distinct entities even after being captured by larger galaxies. Our Milky Way might contain thousands of these dark matter subhalos, each potentially massive enough to gravitationally influence nearby stars or stellar streams. Some astronomers believe they've detected evidence of these subhalos through their gravitational effects on stellar streams, but the detections remain tentative and controversial. The Large Magellanic Cloud, our galaxy's largest satellite galaxy, has provided another window into dark matter distribution. As it orbits through the Milky Way's halo, it creates a wake in the dark matter distribution, similar to the wake behind a ship moving through water. This wake was first predicted by computer simulations and then actually observed in 2021 through careful mapping of stars in the outer halo. The stars aren't moving through dark matter itself, but are responding gravitationally to its distribution, and their positions reveal the presence of the dark matter wake even though the dark matter itself remains invisible. This observation provides direct evidence that dark matter responds dynamically to gravitational forces, flowing and redistributing itself in response to massive objects moving through it. The dark matter puzzle extends beyond our galaxy to the entire universe. Observations of the cosmic microwave background, the afterglow of the Big Bang, show that the universe as a whole is composed of about 5% normal matter, 27% dark matter, and 68% dark energy. Dark matter thus outweighs normal matter by more than 5-to-1 on cosmic scales, consistent with what we observe in galaxies. The cosmic microwave background observations also provide crucial information about when dark matter began to clump together to form the first structures in the universe, setting the stage for galaxy formation. Understanding dark matter is not just an academic exercise. The existence and properties of dark matter have profound implications for the ultimate fate of the universe, the formation of galaxies and stars, and even the possibility of life. Without dark matter, galaxies as we know them could not exist. The additional gravity it provides was essential for matter to clump together in the early universe, forming the first stars and galaxies. Without dark matter, the universe would be a vastly different and likely far emptier place. We owe our existence to this mysterious substance, yet we know almost nothing about what it actually is. Dark matter was first inferred by studying how galaxies rotate. According to Newton's laws, if all, the mass in a galaxy was in the stars we see. Then stars farther from the center should orbit more slowly, just as planets farther from the sun orbit more slowly. But when astronomers measured the velocities of stars at different distances from galactic centers, they found something unexpected. Stars at the edge of galaxies orbit at nearly the same speed as stars closer in. This is only possible if there is a vast halo of unseen mass extending far beyond the visible galaxy, its gravity keeping the outer stars moving fast enough that they don't fall inward. In our own Milky Way, this dark matter halo is thought to extend perhaps 500,000 light-years from the galactic center, roughly 5 times the diameter of the visible stellar disk. The total mass contained in this invisible structure is estimated at between 1 and 2 trillion solar masses, though the exact value remains uncertain. This uncertainty reflects a profound truth. We are trying to weigh something we cannot see, detect only through its influence on things we can observe. Recent research has revealed that this dark matter halo may not be spherical, as once assumed. In 2023, astronomers from Harvard discovered evidence that the Milky Way's dark matter halo is tilted and elongated, shaped somewhat like a football or a zeppelin. This discovery helps explain why our galaxy's stellar disk is warped at its edges, bending upward on one side and downward on the other. The tilt of the dark matter halo, they found, can induce exactly this kind of warp in the stellar disk, solving a puzzle that had persisted for decades. The tilted halo also provides clues about the galaxy's formation history. If the Milky Way had formed in isolation, without major disruptions, its dark matter halo would likely be more spherical and aligned with the stellar disk. The fact that it's tilted suggests a violent past, evidence that our galaxy experienced major collisions with other galaxies. Each collision would have added mass and angular momentum in specific directions, gradually warping and tilting the dark matter distribution. The shape of the invisible halo thus preserves a record of ancient galactic violence. One of the most exciting recent developments involves potential direct detection of dark matter itself. For decades, scientists have observed an excess of gamma rays emanating from the galactic center, a diffuse glow that cannot be fully explained by known sources. Some theoretical models suggest this could be the signature of dark matter particles, annihilating when they collide with each other. If dark matter consists of particles that are their own antiparticles, then when two dark matter particles meet, they would annihilate completely, converting their mass into energy in the form of gamma rays. In November 2025, a study published in the BBC Science Focus reported new observations from NASA's Fermi Gamma Ray Space Telescope revealing a mysterious, halo-like glow of gamma rays around the Milky Way. This glow peaks sharply at energies of about 20 giga-electron-volts, matching predictions for what would be produced if weakly interacting massive particles, a leading dark matter candidate, were annihilating in our galaxy's halo. If confirmed, this would represent the first detection of dark matter through means other than its gravitational effects, a breakthrough that would revolutionize our understanding of the universe. However, alternative explanations remain. Some astronomers suggest the excess gamma rays could come from a previously unrecognized population of millisecond pulsars, rapidly spinning neutron stars that emit beams of radiation. Others propose contributions from cosmic ray interactions or other astrophysical processes. Distinguishing between these possibilities requires careful modeling of all potential sources and additional observations, particularly of the Milky Way's dwarf satellite galaxies. These small galaxies are thought to be extremely rich in dark matter relative to normal matter, making them potentially excellent laboratories for detecting dark matter signals with minimal contamination from ordinary astrophysical sources. The nature of dark matter remains one of the most profound mysteries in physics. Is it composed of particles? If so, what kind? Why doesn't it interact with light? Why is there so much more of it than normal matter? Despite decades of sophisticated experiments trying to detect dark matter particles directly, we have yet to capture definitive evidence in our detectors. The universe is constructed on an invisible scaffold we can barely perceive, held together by forces we don't understand, made of material we've never touched. Imagining that we understand our galaxy when we can only see 15% of its mass is like claiming to understand a house after seeing only the paint on the walls. The violent past. The violent past. Our galaxy did not form in peaceful solitude. It grew through violence, through collisions and cannibalism, consuming smaller galaxies and incorporating their stars into its expanding structure. This process continues today. We can watch it happening in real time, observing the slow-motion destruction of neighboring galaxies as the Milky Way's gravity tears them apart and devours their stellar populations. The clearest example of ongoing galactic cannibalism is the Sagittarius dwarf elliptical galaxy, often abbreviated as SCODE or simply Sagittarius. Discovered in 1994 by British astronomers Rodrigo Ibata, Gerard Gilmore, and Mike Irwin, this small galaxy was hidden from view for so long because it lies on the far side of the Milky Way's central bulge, obscured by the density of foreground stars and interstellar dust. When finally detected through careful analysis of star counts and velocities, it revealed itself as a dwarf galaxy in an advanced state of tidal disruption. Sagittarius orbits through the plane of our galactic disk on a highly inclined, elongated orbit that brings it within about 50,000 light-years of the Milky Way's center. With each passage through the disk, the dwarf galaxy experiences tremendous tidal forces, differential gravitational pull that is stronger on the side nearest the Milky Way than on the side farthest away. These tidal forces stretch the dwarf galaxy, pulling stars away from its main body and forming long streamers that wrap around the Milky Way like ribbons, draped around a maypole. These stolen stars form what astronomers call the Sagittarius stream, visible today as overdensities in star counts at specific locations in the sky. The stream has been traced both in front of and behind the main body of the dwarf galaxy, forming loops that encircle the entire Milky Way. Computer simulations suggest the Sagittarius dwarf has been orbiting our galaxy for at least several billion years, perhaps as long as 10 billion years, gradually surrendering its stellar content with each pass through the disk. The dwarf galaxy may have once been substantially larger, perhaps containing billions of stars, but the Milky Way has been slowly devouring it for eons. What remains today is merely the tightly bound core of what was once a more substantial system. The discovery of the Sagittarius dwarf and its stream revolutionized our understanding of how galaxies grow. It provided direct observational evidence that galaxy cannibalism is not just a theoretical possibility, but an ongoing process. It also raised intriguing questions. If we can see one dwarf galaxy being destroyed right now, how many others have been completely consumed in the past? Their stars now dispersed throughout the Milky Way's halo and thick disk? How much of our galaxy's mass came from accretion of smaller systems rather than from the original proto-galactic cloud? The Large Magellanic Cloud, our galaxy's largest and most prominent satellite galaxy, is another victim in the making. This irregular galaxy, containing roughly 30 billion stars, and visible as a large, fuzzy patch to observers in the southern hemisphere, has long been recognized as gravitationally bound to the Milky Way, but only recently have astronomers realized that it, too, is doomed to eventual consumption. The Large Magellanic Cloud orbits the Milky Way at a distance of approximately 160,000 light-years, accompanied by its smaller companion, the Small Magellanic Cloud. For decades, astronomers debated whether these galaxies were on their first infall toward the Milky Way or whether they had been orbiting for multiple cycles. Recent measurements using data from the Gaia satellite and Hubble Space Telescope have settled this question. The Magellanic Clouds are moving faster than expected, suggesting they're on nearly hyperbolic orbits, meaning this is likely their first passage through the Milky Way's halo. But that first passage will not be a close encounter that flings them back out. Instead, dynamical friction, the gradual loss of energy and angular momentum as the clouds plow through the Milky Way's dark matter halo, will cause their orbits to decay over the next few billion years, eventually leading to a merger. As the Large Magellanic Cloud orbits through the Milky Way's dark matter halo, it creates a wake, a disturbance in the distribution of dark matter and stars, analogous to the wake behind a ship moving through water. This wake was first predicted by computer models and then observed in 2021 through careful mapping of stars in the outer halo. The discovery was made using data from the Gaia satellite and NASA's Near-Earth Object Wide Field Infrared Survey Explorer. Astronomers mapped the positions and motions of over 1,300 red giant stars at vast distances from the galactic center, between 200,000 and 325,000 light-years out, where the stellar halo is extremely sparse and difficult to study. What they found was remarkable: a distinct pathway of stars that forms a wake behind the large Magellanic Cloud, visible as a bright feature in maps of stellar density. The wake consists of stars from the Milky Way's halo that have been gravitationally attracted toward the path of the LMC and now move in patterns influenced by its passage. But the wake is thought to also outline an underlying disturbance in the dark matter distribution. The stars are like leaves floating on the surface of an invisible ocean, their positions shifting with the dark matter below. This observation provides direct evidence that dark matter responds dynamically to gravitational perturbations, flowing and redistributing itself in response to massive objects moving through it. But the large and small Magellanic Clouds and the Sagittarius dwarf are merely the most obvious examples of ongoing galactic cannibalism. These are violent events happening right now, playing out over timescales we can observe and measure. The Milky Way's past, however, is written in the subtle patterns of stars throughout its halo, in the chemical compositions of ancient stellar populations, in the orbits of globular clusters, and in the tenuous streams that trace the paths of long-dead dwarf galaxies. By studying the chemical compositions and orbital characteristics of stars in the Milky Way's halo, astronomers have identified the remnants of dozens of smaller galaxies that were devoured in the past. This field of research, called galactic archaeology, treats the galaxy as an archaeological site where the artifacts are stars, and the task is to reconstruct ancient events from the clues that remain today. Each merger leaves a distinctive signature that can be decoded billions of years after the event occurred. Stars from the same progenitor galaxy share similar chemical abundances, the same ratios of elements forged in supernovae billions of years ago. This is because each galaxy has its own unique chemical evolution history, depending on its mass, star formation rate, and the number of generations of stars that lived and died, enriching the interstellar gas. Additionally, stars from the same merger event tend to move through space along similar orbital paths, because they were all part of the same galaxy before disruption and retain similar velocities and angular momenta. By carefully cataloguing these stellar populations, measuring the chemical abundances of thousands of stars using spectroscopy, and tracking their three-dimensional motions through space using data from the Gaia satellite, astronomers can identify groups of stars that likely came from the same ancient merger. It's detective work on a cosmic scale, piecing together a collision history that spans billions of years from clues written in starlight. One of the most significant ancient mergers has been named Gaia-Enceladus sausage, sometimes abbreviated as GES or simply Enceladus. This collision occurred approximately 10 billion years ago, during the epoch when our galaxy was still actively forming and growing. The Gaia-Enceladus galaxy contained roughly a tenth of the Milky Way's mass at the time, perhaps 20 to 30 billion solar masses, making it a substantial system, though still considerably smaller than the proto-Milky Way. The impact was catastrophic. When Gaia-Enceladus slammed into the young Milky Way, it disrupted the structure of the early galactic disk, heating the existing stellar populations and puffing them up into a thicker configuration. Many of the thick disk stars we observe today may have originated in the thin disk, but were dynamically heated, given higher random velocities, by gravitational interactions during the merger, The collision also delivered a massive influx of stars, gas, and dark matter that significantly increased the Milky Way's mass. Today, remnants of this ancient collision can be found scattered throughout the Milky Way's halo, identifiable by their distinctive chemical signatures and highly elongated, retrograde orbits that carry them far from the galactic plane. The name sausage came from the shape these stars trace out. When their orbital parameters are plotted in certain coordinate systems, they form an elongated sausage-like distribution. The Gaia-Enceladus stars are found throughout the inner halo, and they dominate the stellar populations in certain regions. Spectroscopic surveys have identified thousands of stars that likely originated in this merger, allowing astronomers to reconstruct properties of the Gaia-Enceladus galaxy. Its mass, its chemical composition, even estimates of when and how the collision occurred. Even earlier in the Milky Way's history, approximately 11 billion years ago, an even more massive merger occurred with a galaxy dubbed Kraken. This name was chosen from Norse mythology, where the Kraken was a legendary sea monster, reflecting the enormous impact this collision had on the young Milky Way. Kraken is thought to have been even larger than Gaia-Enceladus, and the collision likely delivered many of the globular clusters that now orbit in the Milky Way's halo. Globular clusters are among the most valuable fossils for galactic archaeology. These dense, spherical collections of stars formed very early in cosmic history, and they are so tightly bound by gravity that they often survive intact even when their host galaxy is completely destroyed. When a dwarf galaxy merges with the Milky Way, its stars typically disperse into the halo over time, but its globular clusters can remain identifiable for billions of years. By studying the orbits and chemical compositions of the Milky Way's globular clusters, astronomers can identify groups that likely came from the same progenitor galaxy. Some clusters show chemical patterns that don't match those of Milky Way stars, suggesting they formed in a different environment before being captured. In 2022, researchers led by Khyati Malhan at the Max Planck Institute for Astronomy created the most comprehensive atlas yet of Milky Way mergers. They systematically analyzed 257 stellar streams, globular clusters, and satellite galaxies using data from the Gaia mission's early third data release. Their statistical analysis used a clever technique based on action variables, mathematical quantities that describe orbits in a way that remains conserved even as stars move through the galaxy. Objects that originated from the same progenitor galaxy should have similar action variables, allowing the researchers to identify groups of associated objects. Their analysis identified 6 major merger events in the Milky Way's history, including one previously unknown collision they named Pontus, after a primordial Greek deity of the sea. This atlas represents a comprehensive reconstruction of our galaxy's violent billion-year history, showing not just that mergers occurred, but which specific objects in today's galaxy came from which ancient mergers. It's the equivalent of looking at a jigsaw puzzle that's been reassembled and figuring out which pieces came from which original picture. Beyond the major named merger events, astronomers have identified dozens of stellar streams throughout the halo, each one the disrupted remnant of either a dwarf galaxy or a globular cluster. These streams are given various names, often related to the constellations through which they pass: the Orphan Stream, the Phoenix Stream, the Tucana Stream, the Chalem Stream, and many others. Each stream tells its own story of destruction and dispersal. Some streams are relatively young and narrow, indicating recent disruption. The GD1 stream, for instance, is the remnant of a globular cluster that was torn apart by tidal forces during its orbit around the Milky Way. This stream is particularly well studied because it's relatively nearby and thin, making it an excellent probe of the Milky Way's gravitational field. In 2018, astronomer Anna Banaka identified a strange gap and spur in the GD1 stream, features that don't fit simple models of tidal disruption. One intriguing possibility is that these features were created by a collision with a clump of dark matter passing through the stream. If confirmed, such interactions could provide clues about whether dark matter is uniformly distributed or clumps into smaller substructures. Other streams are old and diffuse, having been stretched and dispersed over billions of years until they're barely distinguishable from the general halo population. The Helmi stream, discovered in 1999, is an example of an old stream that has been wrapped multiple times around the galaxy. Identifying such ancient streams requires careful analysis of stellar kinematics, the three-dimensional motions of stars, because the spatial coherence has been lost, but the kinematic signature remains. The Monoceros ring is a particularly controversial structure. Initially identified as a ring of stars encircling the galactic disk, it was proposed to be the remnant of a disrupted dwarf galaxy called Canis Major. However, subsequent studies suggested it might instead be a feature of the Milky Way's disk itself, perhaps an oscillation or warp induced by gravitational interactions. The debate over the Monoceros ring's origin continues, highlighting the challenges of interpreting complex structures in the galactic halo, where multiple physical processes can produce similar observational signatures. In 2020, a team using data from the Dark Energy Survey discovered or confirmed the existence of 11 new stellar streams in the Milky Way's halo. This was made possible by the survey's deep imaging of large areas of sky, allowing faint overdensities of stars to be detected against the background halo population. As sky surveys become deeper and cover more area, the census of stellar streams continues to grow, with dozens now known and likely hundreds yet to be discovered. The Southern Stellar Stream Spectroscopic Survey, or S5, has been particularly productive in recent years. This survey uses large telescopes in the southern hemisphere to obtain spectra of stars in known stellar streams, measuring their velocities and chemical compositions. In 2022, the S5 team published detailed results on 12 stellar streams, determining for each one whether it originated from a disrupted dwarf galaxy or from a globular cluster. Dwarf galaxies experience multiple bursts of star formation over their lifetimes, so their stars exhibit a range of ages and chemical compositions. Globular clusters, by contrast, contain stars that all formed around the same time, giving them much more uniform properties. By measuring these properties, astronomers can diagnose the nature of the progenitor even billions of years after its disruption. 6 of the 12 streams studied by S5, Atlas, Alika Uma, Jet, Ophiuchus, Phoenix, Wilka Yaku, and 300S, turn out to be shredded globular clusters, while the other 6, Elqui, Indus, Chelum, Orphan Chenab, Palsa, and Turanburra, are the remains of satellite galaxies. Most of these streams follow prograde orbits, meaning they orbit in the same direction as the Milky Way's rotation. though some follow retrograde orbits in the opposite direction. The distribution of orbital directions provides clues about how the Milky Way acquired its satellites and whether they came in groups or individually. The process of identifying and characterizing stellar streams continues to accelerate as new data becomes available. The Gaia satellite, with its exquisite measurements of stellar positions and motions for over 1 billion stars, has revolutionized this field. Ground-based spectroscopic surveys like Apogee and Gala are providing detailed chemical compositions for millions of stars. Together, these datasets are allowing astronomers to conduct galactic archaeology with unprecedented detail, reconstructing the assembly history of the Milky Way, one merger at a time. What emerges from this work is a picture of a galaxy that grew primarily through the accretion of smaller systems rather than through major mergers with galaxies of comparable size. The Gaia-Enceladus event 10 billion years ago was the last truly major collision our galaxy experienced. Since then, the Milky Way has grown more slowly and peacefully, gradually cannibalizing dwarf galaxies and accumulating gas while maintaining its spiral structure. This relatively quiet recent history distinguishes the Milky Way from some other large spiral galaxies, including our neighbor Andromeda, which appears to have had a more violent and active recent past with multiple significant mergers. The absence of major recent mergers has allowed the Milky Way to develop and maintain its thin disk of young stars and active star formation. In galaxies that have experienced major mergers more recently, the collision typically destroys the thin disk, puffing it up into a thicker configuration or even transforming the galaxy into an elliptical system with no disk at all. The Milky Way's disk is thus a survivor, having avoided catastrophic disruption for the past 10 billion years, a period during which our sun formed, our solar system took shape, and life evolved on Earth. The clearest example is the Sagittarius dwarf elliptical galaxy, a small galaxy currently being torn apart by the Milky Way's tidal forces. Discovered in 1994, this dwarf galaxy orbits through the plane of our galactic disk, and with each passage, more of its stars are stripped away. These stolen stars form long streamers that wrap around the Milky Way like ribbons, visible as overdensities in star counts at specific locations in the sky. Computer simulations suggest the Sagittarius dwarf has been orbiting our galaxy for billions of years, gradually surrendering its stellar content with each pass. It may have once been significantly larger, but the Milky Way has been slowly devouring it for eons. The Large Magellanic Cloud, our galaxy's largest satellite galaxy visible from the southern hemisphere, is another victim in the making. This irregular galaxy, containing roughly 20 billion stars, is gravitationally bound to the Milky Way and will likely be consumed over the next several billion years. As it orbits through our galaxy's dark matter halo, it creates a wake, a disturbance in the distribution of dark matter and stars, like a ship moving through water. This wake was first predicted by computer models and then observed in 2021, providing dramatic confirmation that even invisible dark matter can be tracked through its influence on visible stars. But these ongoing events are merely the latest chapters in a long history of galactic consumption. By studying the chemical compositions and orbital characteristics of stars in the Milky Way's halo, astronomers have identified the remnants of dozens of smaller galaxies that were devoured in the past. Each merger leaves a distinctive signature. Stars from the same progenitor galaxy share similar chemical abundances, the same ratios of elements forged in supernovae billions of years ago, and they move through space along similar orbital paths. By cataloging these stellar populations, astronomers can reconstruct the collision history of our galaxy. One of the most significant ancient mergers has been named Gaia-Enceladus sausage, after the European Space Agency's Gaia satellite that helped identify it. This collision occurred approximately 10 billion years ago, when a galaxy containing roughly a tenth of the Milky Way's mass slammed into our forming galaxy. The impact was catastrophic. It disrupted the structure of the early Milky Way, heating the stellar disk and puffing it up into a thicker configuration. It also delivered a massive influx of stars, gas, and dark matter that significantly increased our galaxy's mass. Today, remnants of this ancient collision can be found scattered throughout the Milky Way's halo, identifiable by their distinctive chemical signatures and highly elongated orbits that carry them far from the galactic plane. Even earlier, approximately 11 billion years ago, the Milky Way merged with a particularly massive galaxy dubbed Kraken. This merger was even more violent than Gaia-Enceladus sausage, and it likely delivered many of the globular clusters that now orbit in the galactic halo. These clusters, dense balls of ancient stars, are some of the oldest structures in our galaxy, survivors from an epoch when the universe itself was in its infancy. In 2022, researchers led by Khyati Malhan created an atlas of Milky Way mergers by systematically analyzing 257 stellar streams, globular clusters, and satellite galaxies using data from the Gaia mission. Their statistical analysis identified 6 major merger events, including one previously unknown collision they named Pontus. This work represents a comprehensive reconstruction of our galaxy's violent billion-year history, piecing together the story of how the Milky Way grew from smaller beginnings into the majestic spiral we inhabit today. The evidence of ancient violence is written everywhere we look. Stellar streams, long tendrils of stars that were once globular clusters or dwarf galaxies, stretch across the halo like the wake of cosmic destruction. The GD1 stream, for instance, is the remnant of a globular cluster, torn apart by tidal forces during its orbit around the galaxy. These streams preserve a fossil record of orbital dynamics, allowing astronomers to map the gravitational field of the Milky Way and search for evidence of dark matter substructures. Some streams show peculiar features, gaps or spurs that suggest gravitational interactions with massive but invisible objects. In 2018, astronomer Anna Banaka identified a strange spur in the GD1 stream, a feature that doesn't fit simple models of tidal disruption. One intriguing possibility is that this spur was created by a collision with a clump of dark matter passing through the stream. If confirmed, such interactions could provide clues about the nature of dark matter and whether it clumps into smaller substructures, as predicted by some theoretical models. The stellar halo itself is a museum of galactic archaeology. Almost all the stars in this region were born in other galaxies that were subsequently consumed by the Milky Way. Their chemical compositions tell us about star formation in the early universe. Their orbital motions reveal the merger history that assembled our galaxy. Some halo stars are among the oldest known objects in the universe, formed when the first galaxies were coalescing from primordial hydrogen and helium. They contain almost no heavy elements, no carbon, no oxygen, no iron, because these elements had not yet been manufactured in significant quantities by stellar nucleosynthesis. A particularly intriguing recent discovery involves the identification of an ancient stellar disk called Pangu, formed more than 13 billion years ago. This disk, containing an estimated 2 billion solar masses of stars, apparently survived the violent mergers that characterized the Milky Way's early history. That such a structure could persist through epochs of galactic collisions suggests that the early Milky Way may have been larger and more massive than previously thought, able to gravitationally dominate smaller infalling galaxies rather than being disrupted by them. Pangu represents the oldest disk population known in our galaxy, a fossil from an age when the universe was less than 1 billion years old. The spiral mystery, and the engines of creation. One of the most beautiful features of our galaxy is also one of the most mysterious: its spiral arms. These graceful structures, which give spiral galaxies their distinctive appearance and have inspired countless artistic representations, are not solid entities like the arms of a starfish, but rather regions of enhanced stellar density. Areas where stars, gas, and dust are more concentrated than in the regions between the arms. As the galaxy rotates, individual stars drift in and out of the arms, somewhat like cars entering and exiting traffic jams on a circular highway. The exact number and configuration of the Milky Way's spiral arms has been a subject of debate and revision over decades of observation. From our location inside the galaxy, mapping the spiral structure is extraordinarily difficult. We cannot step outside to see the pattern from above, and dense clouds of interstellar dust block our view of much of the galactic disk, especially when we try to look through the disk toward regions on the far side of the galaxy. Astronomers must piece together the structure using indirect traces: young luminous stars, regions of active star formation, molecular clouds, and the distribution of neutral hydrogen gas detected through radio observations. Early models of the Milky Way suggested 4 major spiral arms, but observations from NASA's Spitzer Space Telescope in the mid-2000s revealed that our galaxy is actually dominated by just 2 major arms: the Scutum Centaurus arm and the Perseus arm, wrapping off the ends of the central bar. These 2 arms contain the highest densities of both young and old stars, making them the most prominent features in the galactic structure. Between these major arms lie less distinct minor arms, including the Sagittarius arm and the Norma arm, which are primarily filled with gas and pockets of star-forming activity rather than continuous stellar populations. Our Sun resides in what's called the Orion Arm, or the Orion Spur, a relatively minor feature that branches off from the larger Sagittarius Arm. This spur contains the Orion Nebula, one of the nearest major star-forming regions, located about 1,300 light-years away. The Orion Arm extends for about 10,000 light-years and is perhaps 3,000 light-years across, making it a substantial structure but still smaller and less prominent than the major arms. Our location in this spur means we have a somewhat off-center view of the galaxy's grand design, neither in a major arm nor in the quiet region between arms, but in a transitional zone. The question of why spiral arms exist at all puzzled astronomers for decades. In a rotating disk, if the arms were material structures that rotated as solid entities, differential rotation would wind them up over time. Objects closer to the galactic center orbit faster than objects farther out, so any material arm would become increasingly wound and twisted with each rotation, eventually wrapping around the galaxy many times and losing its coherent structure. Yet spiral galaxies maintain their arm patterns for billions of years, suggesting that arms are not material structures at all. The solution to this puzzle came in the 1960s with the development of density wave theory, primarily by astrophysicists Chia Lin and Frank Hsu. According to this theory, spiral arms are not material structures that rotate as solid entities, but rather waves of compression that move through the galactic disk at their own pace, different from the rotation speed of the stars themselves. Think of a traffic jam on a circular highway. Cars enter the jam, slow down, and then exit the other side. But the jam itself remains in roughly the same location or moves at a different speed than the individual cars. In the galactic context, as gas clouds orbit the galaxy, they periodically enter regions of enhanced gravitational pull, the spiral arms, where their orbital velocities cause them to bunch up, increasing the local density. As gas clouds enter these compression zones, they are squeezed, triggering the collapse of molecular clouds and the formation of new stars. The most massive of these newborn stars, brilliant blue giants and supergiants that can be tens or even hundreds of times more massive than the Sun, are extraordinarily luminous but short-lived, typically dying in supernova explosions after only a few million years. Because they remain close to where they formed, these luminous blue stars trace out the spiral arms, creating the appearance of continuous structure. The spiral arms thus act as cosmic assembly lines for star formation. As gas enters an arm, it compresses and fragments, forming clusters of new stars ranging from tiny red dwarfs, barely massive enough to fuse hydrogen, to medium mass stars like our Sun, to the massive blue giants that will dominate the arm's appearance. The blue giants illuminate the arm with their intense ultraviolet radiation, ionizing surrounding hydrogen gas and creating the pink emission nebulae, regions of glowing hydrogen that festoon spiral arms in images of other galaxies. Meanwhile, the lower mass stars, destined to live for billions or even trillions of years, drift out of the arms over time and disperse into the general galactic disk. If we could watch the Milky Way over millions of years with time-lapse photography, we would see stars cycling through the arms like performers stepping on and off a rotating stage. The arms themselves maintaining their overall pattern even as individual stars come and go. The origin of the spiral structure itself remains a subject of active research. Computer simulations suggest that spirals can arise spontaneously from instabilities in rotating disks. A perfectly uniform disk is gravitationally unstable on large scales. Small overdensities will gravitationally attract surrounding material, growing stronger and eventually forming patterns. These patterns then interact with the disk's differential rotation to create spiral features. The central bar also plays a crucial role. Bars are common in spiral galaxies. Surveys suggest that about 2/3 of disk galaxies have bars, and they appear to drive gas inward toward the galactic center while simultaneously organizing the outer disk into spiral patterns through resonances and gravitational torques. Some models suggest that our galaxy contains two different spiral patterns operating at different radii, an inner pattern associated with the bar and rotating relatively quickly, and an outer pattern, whose arms rotate more slowly and are more tightly wound. The Cygnus arm, located between the major arms, might represent a connection between these two patterns. Other models propose that spiral structure can be induced or enhanced by external perturbations, such as galactic collisions. Numerical simulations have shown that the Milky Way may have obtained or amplified its spiral arms, partly as a result of repeated collisions with the Sagittarius dwarf elliptical galaxy. Each time this small galaxy punches through the Milky Way's disk, it creates ripples, density waves that propagate through the disk and reinforce the spiral pattern. If true, then the beauty of our galaxy's spirals is a side effect of violence, an elegant pattern born from cosmic collisions. Recent work has identified what astronomers call the skeletal structure of the Milky Way: dense, filamentary clouds of cold gas and dust that stretch for as much as 1,000 light years, but are only a few light years wide. These structures have aspect ratios of 50:1 or higher, making them extraordinarily elongated, like cosmic filaments or bones. Researchers at the Center for Astrophysics, led by Catherine Zucker, Cara Battersby, and Alyssa Goodman, have argued that these features form a kind of spine for the spiral arms, structural supports upon which the visible features of the arms are built. The skeletal features were identified using infrared surveys that can penetrate dust and detect cold, dense molecular clouds that would be invisible at optical wavelengths. These clouds lie parallel to and very close to the midplane of the galactic disk, precisely where you would expect to find the densest concentrations of star-forming material. Some of these structures have masses of thousands or even tens of thousands of solar masses, all compressed into narrow filaments. The first such feature was spotted in mid-infrared surveys about 5 years before the 2022 publication, and the systematic search identified 10 new candidates, 6 of which meet strict criteria for being true skeletal features. The star formation occurring in these spiral arms is not a smooth, continuous process, but rather happens in bursts and clusters. When a molecular cloud enters a spiral arm and becomes compressed, it doesn't collapse all at once, but rather fragments into smaller clumps, each of which can collapse to form a star or small group of stars. This results in the formation of stellar associations and open clusters, loosely bound groups of stars that share a common origin, but will eventually disperse into the field population. Young stellar associations are large and loosely structured, with typical diameters of about 250 light years. They contain tens to hundreds of young, hot stars that formed from the same parent molecular cloud within the last few million years. The Orion OB1 association, which includes the famous Orion Nebula, is a prime example visible from Earth. These associations are gravitationally unbound. Their self-gravity is insufficient to hold them together, and over a matter of a few million to tens of millions of years, the member stars disperse into surrounding space, becoming separate and unconnected stars in the galactic field. Open clusters are more tightly bound than associations, with typical diameters of a few tens of light years and containing dozens to thousands of stars. The Pleiades, visible to the naked eye as a small fuzzy patch in the constellation Taurus, is a well-known open cluster containing several hundred stars, about 100 million years old. These clusters can survive as coherent entities for hundreds of millions of years, but gradually, gravitational interactions with passing stars and giant molecular clouds disperse their members. Few open clusters survive longer than 1 billion years before dissolving completely,